Swayam Prabha. Digital India. Educated India.
Welcome to the subject Advanced Digital Image Processing and Computer Vision. Today, we will start our discussion on a new topic, that is on feature detection and description. So, let us try to understand what is meant by a feature of an image. First thing is that we consider a feature should be an entity such that it characterizes the visual content of an image. So, as we understand that one of the objective of computer vision is to understand the scene which is in front of the camera, and the scene could be on a two-dimensional plane, it could be on a three-dimensional plane, three-dimensional space. So, finally, what we get in an image, that is the projection of that particular scene on a lower dimensional subspace. In particular, the images which we are considering here, those are two-dimensional images. So, it is a projection on a two-dimensional plane. So, that is the present context. Now, when we consider an image, the whole information that is conveyed to us, that is processed by our visual system, and then also it is processed in our brain, through which we can understand what is there in the image and through which we interpret also the scene whose image is that one. So, if I draw the analogy that our eye is acting like a camera here, and the retina is that image plane where that projection is taking place. But as we understand that this whole arrangement of an image, very low level arrangement where you have the brightness variations over a two-dimensional space. Now, that is not readily, that cannot be used for the information processing. That directly that is not suitable for information processing. Even from the machine's point of view also, we require certain higher level of characterizations. That means when it is simply a pixel with a brightness value, it does not convey the overall organizations what is there in the scene. So, that is why the visual content of a scene is different than the brightness distributions over the image. So, a feature should be something above those pixel level description what we have in the image, and that is why I said that it characterizes its visual content. Now, which means that this content could be it is a part of an organization on describing a region, or as I mentioned that it is a higher level organization than a pixel. We also usually the mathematical form of a feature is that it is a point in a multidimensional space. So, if I consider simply the pixel value, it is simply one dimensional description, that is the brightness value, a content in a particular site of the image which is pixel. But actually, when we consider a feature description which will be describing a particular part of an image, certain regions, or a pixel with its neighboring regions. So, whatever, so that description should be more rich, and we require multidimensional description. So, mathematically it is a vector. So this multidimensional space is usually a vector space for describing the feature of an image. There could be other than numeric representation of different properties or content of the visual content of a particular part. It could be also categorical description, but in most cases, since we are dealing with numbers, even those categories are also represented in a numeric form. But in general, in our case, we will be simply considering a local description or a description of a part to be mapped to a point in a multidimensional real space. So, that is what I mentioned. It's in the form of a n-dimensional vector, we call it feature vector. So, the feature and feature vector is quite synonymous in our context. And as I have shown you that it's a point in an n-dimensional space. So, I hope you have familiar with this notation. It's a Cartesian product of real numbers, which means I set the set of real numbers, and there are n such set Cartesian product. So, it's a coordinate location. Suppose in 2-dimension plane, I will have it r square, where a point could be denoted by just two coordinates x and y. X and y are real numbers, which is a real space. Similarly, for 3-dimension, we will be writing it as r cube, and we will represent a point x, y, z r cube. So, that is how this representation is there, and in n-dimension you can, in general, we use suffixes for n-dimension. So, we will represent a feature vector in terms of a point in that n-dimensional space whose coordinates are given, denoted in this fashion. So, this feature vector, what it could represent? It could represent a point within a neighborhood, it could represent a pattern, it could represent a patch, or it could represent an object, that means the whole object itself using a particular feature vector. Even it could consider representing the visual content of the whole image. So, there are various scenarios by which this representation may happen depending upon your applications, depending upon your requirements. So, what is the role of this feature representation in image analysis? Let us have a very bird's eye view on that part. So, as we have already understand that in your system, so image is your input, and image, as I mentioned, it is a 2-dimensional array, or maybe 3-dimensional array, different kind of imaging system will be there. The first thing what we require, that there are various assumptions on which we try to get our feature representations or understand visual context. So, we need to pre-process image to fit those assumptions. So, image could be noisy also in the environment. So, we need to filter noise, and we need to highlight those relevant portions which are related to the visual content on which we will be interested. So, these are the pre-processing part, and filtering, enhancement, segmentation. So, all those things are related to this kind of pre-processing tasks which we have discussed. And then, of course, come the module of feature extraction. So, you have still the pre-processing module, still the input would be the output would be the processed image, again in the form of the same form of the image itself, either a 2-dimensional array or 3-dimensional array, or it could be multidimensional arrays like satellite images. There are more number of bands. Color images, there are more number of bands, as you understand. So, so these are the this is the processed image, but it is also almost in the similar form. I should say almost, because sometimes there could be a little more variations, where from an image you get an array representation either of higher dimension or lower dimension. But this is also in the form of an array representation, if I say. Then this processed image is used for in the computation module where feature extraction is there. So, there what we get a set of feature vector. So, let me represent this set of feature vectors, say f1, f2 to say fn, and each would be of some multidimensional vector, and their dimensional space may not be also identical, but for the simplicity let us assume that all of them are represented by the same dimensional space. That means all of them are an element of the real space, n-dimensional real space. So, you get a set of such feature vectors, so which actually describes the organization of the image, which describes the visual content of the image, and these are used for the end analysis part depending upon your requirements. For example, if you want the recognition, classification, say object recognition or classification, there you can use this kind of those are the modules whose input would be this set of feature vectors. A bit more clarity with this diagram I have shown once again. As you can see that these are the steps. This is pre-processing input image. From pre-processing, once again you get the processed image as the output, and then you are getting feature. Then it is subject to feature extraction, from where you are getting a set of feature vectors. So this is your output of this model, and then you are using classification, clustering, those kind of techniques. So in a classification, you are trying to, already what are the classes, and you are trying to classify the image to one of these classes. So distinct classes are shown by their color. Or in the clustering, you are not sure that what are the classes, but you are trying to identify the groups of similar features, or groups homogeneous features, or groups, the feature set which has certain kind of similarity, certain kind of relationships among themselves. So a loose way of grouping, and that is called clustering. So that could be also your end object. Now the thing is that this part, that techniques of classification and clustering, where the input is a set of feature vectors and output is and class assignment to the object for which these feature vectors are representing, like images here, or clustering. So these are the tasks we usually deal with the subject which is called machine learning, because you are learning this classifier using this is the context. But there are other kind of learning mechanism, so where actually these feature extractions and also the pre-processing tasks, those are also learned. So just let me explain a little bit here. So actually what you are doing while performing this computation, I mentioned mostly you have seen that you are performing certain kind of filtering. So it is certain kind of filtering that you are performing. That means you are convolving with a impulse response of a system, and that produces your output. Even the feature vector also, you may consider that finally they are represented from a set of filter responses. That means they are also filters. So what you essentially design, few filters, and depending upon your requirements, and this can be designed by doing some analysis over your the properties of the images what you have, and your relationships with the final task. So these filters could be pre-designed. We call them handcrafted filters that you are using, and then it gives you the set of feature vectors. And now this becomes your learning task, starts with this input of a set of feature vectors. And there are these machine learning techniques, like you can use support vector machines, you can use various Bayesian classification approaches, decision tree. There are different kinds of learning paradigms by which you can design these classifiers, or different clustering techniques by which you can find out those groups. But what you can do instead, even these filters could be also learned, and that is the domain that is very interesting, and that is what has become the very active area of research, and we found wonderful applications of image processing and computer vision in various fields of science and technology. And this learning mechanism is called deep learning. So the term deep comes from a different connotation. It is not that we are learning, since we are learning all these stages, in a way it is related, but this term deep comes from, actually we can map this kind of learning task with a kind of classifier which is called neural network classifier, which can be designed, trained specifically under the machine learning paradigm. Again, same neural network framework can be also trained under the deep learning paradigm, where you are learning everything. You are learning from your pre-processing filters, then filters for feature extractions, then of course, then the final classifiers, everything under this same neural network paradigm. So that's very interesting, and that makes computational part convenient and tractable. So so this is how, this is the overall picture by which the features play an important role. Either you learn it or you compute it through your pre-designed set of computations. So some of the typical problems regarding this, that also let us just have a brief idea. Say you want to determine structure or geometry of objects, or to determine material properties of objects, to determine an object's position, category and its role or interaction with other objects, or to find similar images from a library given a query image. Consider this particular example of structure recovery. Say you can see that there are two images of a same scene. So this is a Greek temple of Neptune basically, and it was near Athens, and this photograph I have taken from two different views. And the idea is that you want to recover the three-dimensional structure, because you have the two-dimensional descriptor from a projection, from different projections of the scene, but can you build up a three-dimensional descriptions, the coordinates in a 3D space? So for that there are techniques, and in fact in this particular subject we will be dealing with that kind of techniques later on. So one of the key idea is there that you try to understand that which are the same point in the scene, and if you can get can establish that relationships, now with some additional informations regarding imaging system, you can get the three-dimensional coordinate of that point, and you can that's how you can get the three-dimensional description. So the problem here would be said in this way, that given two views of the scene, recover the unknown camera displacement and 3D scene structure. Consider another problem. Say it's a karyotyping problem, and the problem is that, say you have homologous chromosomes in our cell, and there are microscopic images of the nucleus of the cell, and there, as you know, at a certain stage of cell division, these chromosomes, they are visible with certain kind of staining, and they form certain bands. So you might have seen, take this particular example, you can see that there are different band patterns, and these band patterns are distinct, or distinct enough to say that which numbered chromosome it is. What is it? That when during cell division, these chromosomes are linearly ordered just before the division, and there certain orderings give them numbers. So we identify chromosomes with certain numbers. And one of the objective of but this is not, still it is not in that stage. It is not. So you cannot since the ordering is not there, it is a mass and it is scattered in an arbitrary way. So one of the objective is that to identify the chromosome with the corresponding corresponding numbered chromosome in our understanding when there is so that gives various clues to the biologist or to the doctors, clinicians, that if there is any abnormality, if there are multiple copies, etc. So for the convenience of the doctors, one of the things we need to do, we need to arrange them in some good order, where these numbers and also homologous pairs, because they occur in pairs, so they can be placed in this order. Actually, what is done also clinically, the corresponding pathologist who does this kind of study, they do it manually. They are expert, so they can find out that which are the chromosomes which correspond to, say for example, each other, and they will try to put them. There is a interactive visual tool by which they can select and they can put them into the into this kind of arrangement, and later on they try to see whether there is any kind of abnormalities, etc. So, so this task, can you automate it? So those manual operations, can you automate it? So that is what is called pairing of homologous chromosomes. One of the interesting thing, you may find that you may consider this is a two-dimensional image because you are taking a microscopic image, but you know that actual scene is three-dimensional. There are various foldings. You can see there are various foldings happen itself within that in that image, which means that it's a three-dimensional structure which is being folded, but those are the challenges are there in this problem. So this is also one kind of problem related to computer vision or image processing, and you understand now the feature descriptor has to be suitable, appropriate for solving this problem. Let's consider the third example. This is, say, we want to find out the material property from remote sensing images. Say we can see that this is a remote sensing image, and this may be pseudo colored image after certain processing, and then we want to find out that what are the properties like asphalt road, as it is shown here, asphalt road, or green vegetation or dry vegetation. So can you do it automatically? So this could be another problem under this context. Document analysis is also could be another example where you would like to find out the spatial arrangement. Say this is a scanned document of a page of a book, and whether we can get the arrangements, like say these are the paragraphs, say this is a column, so this is a double column, so this is the left column, say this is the right column, whether we can find them out. Then what about the title part, this arrangement, and further for each one, can you get all the sentences and text from them? So all these so this is the document analysis. So this is another areas of research and applications for processing. Scene matching is a sub-task of the problem what I mentioned about understanding the structure. There the objective is that we would like to build up the correspondence between similar points, and there are various challenges, because as you understand that these descriptions, because you are getting projections in different angles, so the local descriptions they vary. But is there any way we can make them invariant, make certain descriptor invariant, so that they are easy to detect and they are easy to easy for matching or establishment of building correspondences. So here there are various kind of transformations it may happen. It is from different views, or same image could be translated, rotated. There could be it could be the scale variations, that means it is taken from a distance. So how to establish these correspondences? So these are certain steps what is required there, like you need a detection. So when you are going to describe certain certain part or certain organization, so how do you get derive those organization, those parts which are remaining invariant, which are easy or which are very distinct, and which is you are going to find those kind of descriptions even after different transformation. So that is the detection part. Say I want, so for example, if I consider a description here, as you can see that there are various places where this description could match, and so it's not an unique descriptor of an image, unique content of an image, and it is very difficult whether this region corresponds to this or this region corresponds to this. But if I consider this one, so that descriptor probably it has certain uniqueness, though there are no similar kind of things might be there, right? I mean, though there are certain ambiguities, but still, no, it has better, distinction than many other kind of regions. So, what are those parts? And we call for the point descriptor, we call them key points. So, what are those points or key points which are likely to be found in both the views and whose description also could be very distinctive from others. So, this is the problem of both detection and description. If we can do it very efficiently, then the matching part is that, as I was mentioned, that this part and this part, they and this part and also this part, they look similar. So, how can you design certain techniques by which you can exactly put matching of this and this? So, you can resolve further, you can do further resolutions of pairing up of this kind of points, key points from multiple scenes. So, with this kind of introduction, let me just discuss some of the techniques for feature detection and descriptor. So, we will start with the point descriptor, and I should say the point detector in that sense. So, one of the thing, as I was mentioning earlier also with that example, that when we consider a point, first thing we would like to see that how distinctive is that point considering its arrangement, overall organization of the image, so that in multiple views also, in different transformation also, that distinctiveness is still preserved, so that you can identify those points. So, for example, here is a thing is there that say this is a region. Now, this is a very homogeneous region. Now, this region has so many different candidate region in the other scene. If I consider an edge, for example, an edge point, now it has less number of candidates. That means I can consider, and also this edge also has certain orientation, if I say. But once again, I mentioned that it could be transformation, could be also oriented. So, anyway, but these candidates would be always over these parts. So, any of these points, there we can identify them as edge, and but there are still a good number of points which could be a matching point of this one. But let us consider this particular corner point or the edges where they meet. You can see that with respect to this diagram, of course, there is only one corner, but there could be also in different scenes, you could have multiple number of edges meeting. For example, let us consider a triangle here, right? So, there could be various possibilities of corners. So, you can have more number of corners, but the point here is that those are more distinctive than the other kinds of features. Now, one way we try to measure this kind of distinctiveness is that how the variation takes place if we just move around the neighborhood. So, here in this part, just tries to show that if I consider a point, say central point, and around this neighborhood, if I move in any direction and consider the variation, say I take the sum of square of values, that is the measure. So, there is one particular measure, say sum of square of pixel values. So, it is a kind of energy measure, sum of square of all pixel values around this neighborhood. Now, if I move along any direction, now that value will remain mostly the same, as we can understand. This distribution still is the same. Whereas, consider this one at the central point, and if I move along these directions, there would be some variation. If I move along this direction, these directions, this sum of squares of those pixel values will have some variation. But if I move along this direction or this direction, you understand that that variation won't be there, right? So, it has certain, in some directions it varies, but in some directions it does not vary much. So it has this kind of property, and these are the properties by which we try to distinguish that whether it's a point on an edge, whether it's a point on a homogeneous region, or if I consider a point just the corner, centering that corner. Now you can see if I move along any direction, there would be some changes. In some changes, there would be in some directions the change would be quite high, in some directions change would be low. Like here also in these directions the changes are high, but in other directions changes are low. And in this case, whatever, there would be some significant change, though there would be variation. So this this property we are using while doing the feature vector. So mathematically, let us see that how this analysis is carried out, and from there, what is the mathematical operations which could distinguish this kind of distinctiveness of different kinds of features, and take those features whose variations could be observed because of this kind of neighborhood changes, and those features we are calling it key points, those points. So this is the key point in this context, in this example. So we call this region as flat region, say this region as edge region, and this region as corner region that we mentioned, and corners are considered as the key points. So this computation, let us see that how we can carry out this computation. You consider shifting the window by a vector uv. So the same thing I was mentioning, say you have a point here, feature point here, and we are moving this by a vector, say w is shown here. This w is the window, and this feature vector is uv. Now since I am moving it, I am just saying that window is being moved because all points are parallelly moved by the same amount. So this rectangle or square, whatever zone, is being moved here. So from here, this center is moved, say for example here, and this is the region. So what I would do, I would simply take the difference between sum of squares of these two regions. So they compare each pixel, summing up the squared differences. So how do you express the sum of square? Say that, say this is a pixel. So whatever pixel is there in that window, let me express the coordinate of this pixel. Any pixel is a element of that window. So w, let us consider it's a set of pixels. So if I consider is sum of square, what I will take simply the square of that pixel and consider all x and y such that x and y is an element of w. So that is my, I should say, that is the sum of square here. Okay, so let me write it as say w. This is the sum of square. But when we are taking the difference, so what I will do, that I will basically take the sum of square of the differences. That means it has a correspondence. So this xy location is shifted here to, say this is an xy. So when it is a vector uv, xy is shifted to as x plus u and y plus v. So what I will do here, so what I will rather do, that I will consider the difference between these two pixel values and take the square of it, instead of just taking the difference between sum of squares. I will take the square of the differences here. I could have taken the difference between sum of squares, but this is what I will do here. So this is one of the measure, and this error measure I will be considering, so error is usually denoted by a symbol E. It could be S also, there is no issue, but let us consider some standard notations what is being followed usually to denote the error. So, we consider EUV is the respective error. So, this is the definition. So, this is the error term. So, we are expecting this because of the change of UV, we get EUV, this change, and what we require that this change should be significant in all UV. So, our objective would be to measure the, as you say, so what is the, say if I consider all UV, a set of, so consider all such UV directions, that means these directions, these directions, these directions, in every possible U and V you are considering, and with some restrictions of say UV within that particular zone. So, in that set, if I have to find out what is the minimum change, because this minimum change should be high. If the minimum change is high, which means all other changes are also quite high, because higher than that value. So, if the minimum change is significant, so what I need to find out that whatever UV vector you can define, that means if it's a discrete space, so centering this point, I will move to different directions. So, these are my set of UV. Okay. So, let me also define this set of UV, again a coordinate in W. So, whatever points directions are there in the W, I am moving there. So, this is my minimum error, and I would like to take those points where this minimum error is significantly high. So, that is the principle, but let us see how this computation is carried out by doing some differential analysis, differential calculus, analytical through analytical differential geometry, or through our analysis, how this computation is done. So, as I was mentioning that we define this error as sum of squared differences, and this is given by this one. So, same expression, as you can see, this is what is given, and this is the error in the direction U and V. So, just let us try to understand first that with U and V, how this value is going to change. So, if I use the Taylor series expansion for multidimensional function, and I would restrict my operation till the first derivative, then it becomes very simple. So, you can see that it is simply the extension of one dimensional quantity into multidimension, and this is a partial derivative with respect to x and partial derivative with respect to y, and these are the steps. U is the movement along x, u amount of step, and v is the movement along y, v amount of step. So, that is we call it delta x and delta y in our jargon of calculus, those terms. So, u and v is simply that delta step. So, u is delta x and v is delta y. So, we can write it in this fashion, and we are ignoring the higher order terms. It makes my mathematics also very simple, because if I can perform, for small u and v, I can always approximate, I can ignore those higher order term, and I can approximate this expression in this form. And then this also can be written in the vector notations or matrix notations, the column vector notations. Say in the column vector, uv is the direction of displacement. So, this is my column vector, uv is the direction of displacement, and then the derivatives or gradients along x and y. Now, I have put it as row vector, which means if I write it in this way, ix Iy is also my derivative vector. So, I will perform the transpose to get this row vector. And these are the notations. Just to note that Ix is actually derivative of I with respect to x. This is the notation we are using. Similarly, so let us again proceed. So, this is the notation. So, now you can see that how the whole analysis can be reduced to a simple expression like this. See, you have this difference, and then if I replace this with this one, so this Ixy and Ixy gets cancelled. So, finally, you find out this quantity. Now, this quantity, as you know that if x is a column vector, so if I write magnitude of x square, I can also write it as x transpose x. If it is a column vector, if it is a row vector, then I should write it as x transpose. So, you please note our notations, we are mostly dealing with column vector. So, I will be writing this particular thing in this fashion. So, this part is like the column vector. So, this is a transpose, and then this one is the other vector. So, once we perform the transpose operation, as you know that this transpose operation means, say, if I have two vectors A, B transpose, this is B transpose A transpose. This is a relationship with the matrix multiplication. So, UV, this column vector, after transposition, it becomes a row vector UV, and this Ix, Iy, this was a row vector, it becomes a column vector, and this becomes a row vector, and this was already row. So, finally, since matrix operation is associative operations, we perform the multiplication of these two quantities. So, which will give us these are the terms. Okay. So, we can see that it's a kind of a quadratic form by which these expressions can be expressed, reduced to in this form. So, we can write this expression. This is the expression we can get. So, finally, you can see with varying UV, because as I mentioned that our objective is to find out what is the minimum change that is taking place. So, with varying UV, this quantity will be determining, say, for any UV, this is the quantity which is independent of the values of U and V. This is the characterizations of that local distribution. This is the square of the derivative with respect to x, this is square of the derivative with respect to y, this is the multiplication of derivatives, and this one is there. So, this quantity is interesting, and since it is a quadratic expression, we can show that at certain directions you will have the maximum value, and in certain directions we will have the minimum value by doing actually the eigen analysis of this particular matrix, this 2 into 2 matrix. So, if I perform the eigen analysis, the eigen vectors, they would provide me the directions of minimum change and maximum change, and eigen values, they would provide me the amount of change. So, the minimum eigen value, that would give me this particular quantity, that is the minimum change. So, this is very methodical standard analysis by which very conveniently we can exploit the local statistics neighboring this point xy, and from there we can find out that what is the minimum amount of change. Not only that, what are the directions along which those changes take place. So, this I will continue once again, this what I said. So, so this is just giving example that if it is moved along UV, so directions for the largest and smallest U values, that we will be considering. And this matrix, let me denote it as by the matrix H and eigenvectors of H, that would give us the direction of those changes. So, the eigenvectors of a matrix A are the vectors X that satisfy, this is standard from our standard algebraic results. So, from the matrix algebra itself. So, if I take the determinant, if I solve this equation, then the values will be the eigenvalues, and if I put those values in this equation, then we will get a vector, because there will be redundant equations. You cannot solve those two equations, but you will get a vector out of that. So this is a simple case because it's 2 cross 2. So, the computation of determinant is also very simple. It's a product of this quantity. So, finally, you can see that your eigenvalues would be this one, and eigenvector you have to solve this problem, and you can find out the corresponding eigenvector. So, this is a summary that defines shifts with the smallest and largest changes of this, and the direction of largest increase in E and amount of increase in direction x plus, direction of smallest increase in E and amount of increase in direction x minus. But finally, our objective is to find out the smallest change, because that smallest change should be sufficiently high. So, that is what we will arch for small shifts in all directions. So, the minimum of EUV should be large. So, I mentioned these things earlier also, and that is given by the minimum eigenvalue of this matrix H. So, some of the examples could be there. Say you have this kind of image. For the convenience, we have taken this kind of image as an example, and these are the chessboard pattern. As you can see, these are chessboard pattern. There are black boxes and white boxes, and if I consider the points or with the maximum eigenvalue, which are I should say which crosses certain threshold. So, it just shows the maximum eigenvalues. Simply it shows maximum eigenvalues with some scaling, and you can see that these edges are also coming, because along those direction of edge, in fact the perpendicular direction of edge, the changes are maximum. So, edge points are also coming. But if I consider even the minimum should be also quite high, anyway, that if I scale them, this is a minimum distributions. That means for each points, this minimum value is quite small. Around these points, minimum value is quite small. Only the junctions, there we have significant minimum values, and that has been scaled. You may notice that there is certain kind of distribution. So, the feature detection algorithm could be simply stated in this fashion, that we compute the gradient at each point in the image, which means I have to compute these quantities Ix and Iy, and then I have to take the neighborhood statistics. So, if I say that Ix square, actually what I should do after computing Ix square, I should perform the average of Ix square. So, usually we do it by Gaussian smoothing and take the average. Similarly, I compute Iy square and take the average, and then I compute Ix, take the average, compute. So, from Ix, Iy, I compute Ix square, Iy square, and then I take always the average, and then I multiply, because otherwise, if I consider a matrix, you can see that the respective determinant of this matrix is equal to 0, and then you will have a problem with this this finding out of the eigenvalues. So, you should take the averages and then use these computations, because you assume there is a noise. So, that is what I mentioned, that you take those point computations of derivatives, square them, but take the averages around the neighborhood, and then you compute the eigenvalues of H, and then locate points with large response for your minimum eigenvalue, which is greater than certain threshold. So those are the points are your key points, or those are the detected feature points, and selects points where actually we consider a local maximum. It is not local maximum should be more precise. So instead of taking the always at the threshold, what happens that near about this point also, in some neighborhood, still you will get significant value for minimum eigenvalue. But if I take the local maxima, it is precisely a point which having where the local maxima takes place, and those points are considered as a feature point. So here we have illustrated that how a neighborhood of a point where the where we will find out the distribution of the minimum eigenvalue, how it looks. As you can see that it takes certain kind of this kind of pattern for that image. So the local maxima should be at the very center of this pattern. So that's why we are interested to find out local maxima instead of just putting a threshold. So points with local maxima is your point of interest. So this operator is known as Harris operator. When we say operator, actually we will give you also mathematical expressions for computing that measure. So a operator is a kind of mathematical function on a particular quantity, and then it provides a value, okay, with that operations. So which will be the some kind of proportional value of the minimum eigenvalue, either proportion or it's a monotonically increasing function kind of thing. So this is one of the Harris operators form. So instead of just giving the minimum eigenvalue, we would give you a ratio of product of eigenvalues. So you can see that if the minimum eigenvalue is strong, then this value would be quite high, because this product will be finally dominating the things. If the minimum eigenvalue is small, then this value will be also small. Now the advantage you have when you give this kind of product and also sum, just from the Harris matrix itself, like you can get determinant of H as the product and trace of H as the trace of H is the sum of the diagonal element, which means that if I have these quantities ix square, iy square, ix, iy, product here also ix, iy. So the determinant could be written as minus this is what is determinant, and trace would be simply the sum of those diagonal elements. This is the trace. So the ratio of these two. So the ratio of these two will be the value, will give us the value which is the value from the Harris operator. So this function is called the Harris operator, and that is what you can use for computing the key points of a positions. So this is the definition, as I mentioned. Trace is sum of the diagonal elements, and product is basically the determinant. So very similar to the minimum eigenvalue, but less expensive because you are not performing any square root operation. So square root operation is expensive computations in the computer. So so the sum and product is is a less expensive operations. So we consider all these kind of things, because in an application when you are computing these points, there would be number of points, so millions of points you may have to compute, and think about the cost if you can save using simply this determinant and trace instead of finding out minimum eigenvalue, because square root is an expensive operation in terms of number of cycles that would take to compute it. So this operator is also called Harris corner detector or Harris operator, as I mentioned. There would be many other detectors like this on the similar principle, but this one is a very popular detector. So, some example where I can show once again, you can see that how these two are related, that minimum eigenvalue and Harris operator. Say this distributions, this is for the minimum eigenvalue and this is for the Harris operators distributions. They are quite similar distributions considering a particular neighborhood. So, there is an example of this Harris detector. Say if you have this image, these F values are obtained like this, and from where you get this local maxima, that would give you the respective key points. So, you can see that you get very precise positions by which these key points are shown here. So, actually, so this is how the key points are computed, but once we want to establish the correspondence between the key points of two images, now there could be multiple candidates, as I mentioned. Now, the problem by which you would like to know the task what is required is that how do you build up these correspondences of these key points. So, we call this task as feature matching. So, the example is something like that. Say you can see that there are certain key points here. Now, it may not be very visible here because these key points are very small, very minutely, if you can observe, it is there from the previous case. So, how do you establish these correspondences? And for that you require the descriptions of these key points. So, just position of the key point does not give you the descriptor. So, all these key points, they look at least from the point wise they are all similar candidates. Any one of them could be a candidate. But when you consider a particular key point, say this key point is a key point and its local statistics, neighboring statistics is quite distinctive than say this one. So, in the respective image, when this statistics, if we can somehow capture where there is a similarity between the statistics, then we can establish this kind of correspondences. So, that is the task of feature description, and that is what we will be considering in next step. That means it is detect the feature points in both images, which I discussed using an operator like Harris operator. Then how do you describe those key points by their local statistics? And of course, we finally use some matching technique to build up the correspondences, like some kind of distance measure you can use, where the distances are small, you can say they are likely candidate for becoming the corresponding pair. So, let me stop here today and we will continue this discussion once again, particularly the methods of describing the features or the point features, but here what is presently being discussed in our next lecture. Thank you very much for your listening and your patience.